Quantum computers process information using quantum gates, the building blocks of every quantum computation. For these quantum gates to work optimally, they need to be precisely accurate and be optimized perfectly. Most quantum gate optimizers in this world share this one assumption that the hardware will work the same in the end of an experiment as it did in the start. It doesn't. I am Sashreek Satapathy, and this is Fidelity Aware Drift Embedded Gate Optimization, also known as FADE. The two dominant gate optimizers, GRAPE, Gradient Ascent Pulse Engineering, and CRAB, Job Random Basis Optimization, both compute their pulses against a fixed Hamiltonian, the one measured at calibration. But superconducting qubits differ from flicker noise, which is 1 upon f flux noise. Trapped ions differ from laser fluctuations. A gate at 99.9% fidelity at 9 am can degrade meaningfully by 9:30, and no optimizer in this field accounts for that. Drift has always been treated as someone else's problem, patched by recalibrating more often. Fade argues it's a flaw in how we've been posing the optimization itself. My research question is this: can an objective function that explicitly models time dependent hardware drift produce control pulses that sustain higher gate fidelity across a full experimental session than conventional single shot optimizers? The independent variable is the structure of the objective itself. The dependent variable is the gate accuracy over time and not at a snapshot. If the answer is yes, fidelity degradation is partly a consequence of how we have framed the problem, and that means we can design our way out of it. FADE runs in three phases. First, a gap analysis of every quantum control and ML optimization method, mapped by objective class and Hamiltonian assumptions. No such mapping exists. That's an independent contribution. Second, the framework. I extend the Lindblad master equation with a stochastic Hamiltonian, h of t equals h naught plus delta h of t and c. The objective j theta integrates expected fidelity across the full session, penalizing pulses that drop below the 0.99 threshold. Gradients from GRAPE refine the pulses. Bayesian optimization tunes the drift module. Third, benchmarking fade against GRAPE and CRAB on Q-tip. Two platforms: superconducting transmon, trapped ion qubit, three metrics: session fidelity, variance, recalibration frequency. NISC. Noisy intermediate scale quantum devices have no error correction. Every gate error accumulates. FADE shifts gate design from optimizing a snapshot to sustaining accuracy across an entire computation. The field asked how to maximize fidelity at one moment. FADE asked how to sustain it.